students. In this video we are going to start introduction to linear transformation. Introduction to linear transformation. First we will see what is a transformation. Definition. A transformation or function or mapping, a function or mapping T from Rn to Rn is a rule that assigns to each vector x bar in Rn a vector T of x bar in Rn. Okay. The set Rn is called domain of T, and Rm is called the codomain of T. The notation T from Rn to Rn indicates okay, here no need to write down this, only remember that this Rn is domain and this Rn is a codomain. Okay. For x bar in Rn, the vector T of x bar in Rn is called image of x bar under the action of T. T of x bar is image of x bar. The set of all images T of x bar in Rn is called range of T. Okay. See here, what is a transformation? Suppose this is a set Rn and suppose this is a set Rm. Okay. Instead take here x and 1. Okay. Suppose here is x in this capital X. When we apply T on this x, so you will get T of x in codomain. This is a domain and this is a codomain. Okay. And this T of x bar is called image of x bar under the action of T, and the set of all images of T of x bar in this codomain is called range of T. Suppose here is x1, x2 and here is x3. And here images are x1 bar, x2 bar, T of x3 bar. Then range of T is T of x1 bar, T of x2 bar and T of x3 bar. Okay. Let us take next definition of linear transformation. Definition. A transformation T is called linear if first one is T of u bar plus v bar is equal to T of u bar plus T of v bar for all u bar comma v bar in the domain of T. Okay. And second is T into alpha u bar is equal to alpha into T of u bar for all u bar and all scalars alpha. Okay. A transformation T is linear if T satisfies these two properties. Okay. Write down one note. Every matrix transformation is a linear transformation. Every matrix transformation is a linear transformation. For if A is m by n matrix, then the transformation T from Rn to Rn given by T of x bar is equal to A into x bar. X bar belongs to Rn. We have for any x bar comma y bar belongs to Rn, T of x bar plus y bar. We have to satisfy these two properties. T of x bar plus y bar. We have to show that T of u bar. We have to show that T of x bar plus y bar is equal to T of x bar plus T of y bar. Okay. Here T is defined as T of x bar is equals to A into x bar. So T of x bar plus y bar is equals to A into x bar plus y bar. Okay. By definition of T, which is equals to, here you can give reason, by definition of T. Okay. This can be written as A into x bar plus A into y bar. Use again definition of T. Here is T of x bar plus T of y bar. Okay. So we will get T of x bar plus y bar is equal to T of x bar plus T of y bar. Okay. Now we have to prove second property. For any scalar alpha, T of alpha into x bar, which is equal to, use here capital X bar Okay. Capital X bar and capital Y bar. T of alpha into x bar is equal to this. By definition of T, this can be written as alpha into x bar. Okay. Alpha is a scalar, so take it outside. Alpha into a into x bar. Okay. This is nothing but T of x bar. So two properties of linear transformation is satisfied. So every matrix transformation is a linear transformation. Okay. Let us take some examples of linear transformation. First example is a transformation T from Rn to Rn given by T of x bar is equal to x bar is linear and is known as identity linear transformation linear transformation. Okay. Second example is a transformation T from Rn to Rn here is n. Rn to Rn given by T of x bar is equal to 0 bar for all x bar belongs to Rn is linear and is called zero linear transformation Third example is given any scalar alpha define T from Rn to Rn by T of x bar is equal to alpha into x bar in Rn is linear. Okay. We will prove this example for any x bar comma y bar in Rn. T of x bar plus y bar which is equal to alpha into x bar plus y bar, which is equal to alpha into x bar plus alpha into y bar. This is a T of x bar, alpha into, this is a T of x bar plus T of y bar. First property is true. This is first property. For second property, consider T of alpha into x bar. So this is T of alpha into x bar. This is alpha, suppose here we will take c into x bar. So here you will get alpha into c into x bar. But c is scalar, so this is alpha c into x bar. Okay, alpha c into x bar, which is equals to c alpha into x bar, which is equals to c into alpha x bar, which is equals to c into t of x bar. So here t of x bar is equals to alpha into x bar is a linear transformation. Okay. If 0 is strictly less than, alpha is less than or equal to 1, in this example, at this note, T is called contraction, and it is called dilation. It is called dilation if alpha is greater than 1. Okay. Take one example. In particular, T from R2 to R2 given by T of x bar is equals to alpha into x bar. X bar belongs to R2 and alpha scalar, and alpha is scalar. If alpha is equals to 1 by 2 and suppose x bar is equals to matrix 2, 3, then T of x bar is equals to 1 by 2 into x bar, because your transformation is T of x bar is equals to alpha into x bar. So T of here alpha is 1 by 2, so T of x bar is equals to 1 by 2 into x bar. 1 by 2 into x bar is 2, 3, which is nothing but 1, 3 by 2. Okay. So here your alpha is less than 1, so T is called contraction. So here your vector is contracted. Next, therefore the T contract the vector x bar. Okay. If alpha is equals to 2 means which is greater than 1, and again x bar is same 2, 3, then T of x bar is equals to 2 into x bar, which is equals to 2 into 2, 3, which is nothing but 4, 6. Here T dilates the vector x bar, means T expands the vector x bar. Okay. Therefore T dilates vector x bar. Okay. These are the examples of linear transformation. Simple properties of linear transformation. Simple properties of linear transformation. Simple properties of linear transformation. Let T be a linear transformation. Let T be a linear transformation. Let T be a linear transformation. Then first property is T of 0 bar is equal to 0 bar. That is T transform 0 vector